So suppose you are a gas molecule. There are a lot of other gas molecules around you, and due to temperature, you move around, and so does your partners. And eventually, you collide with one of them. The question is, how long does it take? To be specific, we're asking, how long did it take between successive collisions? Now, to answer this question, you may think we need some physics tools. For example, you may think we need to calculate the force between molecules. Either this is because of gravitational force or some other kinds of van der Waals force. You may also think we need the Boltzmann distribution. That is, we need to calculate how the velocities of the molecules are distributed. Also, you may think we need the kinetic theory of gases, because we're dealing with gases at a certain temperature after all. And also, you may think we need the elastic collision formula, which makes things so complicated. However, the truth is, this problem doesn't have that much to do with physics. Instead, we can approach it just from a probabilistic perspective. Yeah, so it's just math, no physics. How's this even possible? Today, we are going to analyze the mean scatter time from a probabilistic perspective. The mean scatter time is just the answer to the question of how long did it take. To be specific, we're asking the time needed between successive collisions. So just picture this in your head. You are a gas molecule moving around with other gas molecules, so you eventually collide. Alright, we just said that we are going to analyze it in a probabilistic perspective, so we need to define the probability. This probability will be a function of time, so we write it in the function p of t. Now, we need to define the meaning of this function. What is it? Well, it's the probability of you not colliding with another gas molecule from time 0 to time t. I think you understand it. It's pretty easy to grasp. So, let's ask ourselves, what is the probability after a small time interval? This is very important because collisions happen from time to time, so we need to find the probability as a function of time. Let's call this time interval dt. What is p of t plus dt? Well, we can write this equation. I'm going to convince you that this makes sense. You can try imagining canceling out the dt. So the last term is just dp. Now, in dt, d just means a very small time interval. So dp must mean a very small change in probability. Now, the probability at time t plus a small change in probability equals the probability at t plus dt. Makes so much sense. So, I'll just put the dt back there. Alright, so remember this picture? Now, we are going to analyze it from a 3D perspective. In time dt, you sweep out a volume. What's this volume? It's a cylinder. The height of the cylinder must be your velocity times the time elapsed, so it's v dt. Let's suppose that you have a cross-sectional area of sigma. Also, we will suppose that the density of molecules is n. That is, there are n molecules per unit volume. The question is, what is the number of molecules in this volume? It's actually pretty easy to understand. There are n molecules per unit volume, while the volume of this cylinder is sigma times v dt. So the answer is n sigma v dt. Okay, why is this even important? Recall that we have this equation describing the probability from time t to time t plus dt. Recall that p is just the probability of you not colliding from time 0 to time t. Now, we can find another way of writing p of t plus dt. What is it? Well, p of t plus dt is just p of t, that is the probability of you not colliding from 0 to t, times the probability of not colliding from time t to t plus dt. And the term in parentheses is just 1 minus the probability of you colliding. because 1 is the total probability, and the probability of colliding in dt just equals the number of molecules you should encounter in dt. Just imagine this. If you are expected to encounter one molecule in dt, it means that you are sure to collide with another molecule. So the probability of you surviving this dt is 0. So this term makes sense. So mathematically, we can write it this way. We have two equations describing p of t plus dt, so we'll set them equal. We can solve this equation to find this ordinary differential equation, which can be solved very easily. I'll just quote the solution here. The probability is this number e to the negative n sigma vt power, where e is just the usual 2.71828 number. So we have found the probability of you not colliding with another gas molecule from time 0 to time t. You can make sense of this by plugging t equals 0. When t equals 0, the exponential term becomes 1. So the probability of you not colliding is 1, of course, because you haven't even started moving. Alright, aren't we supposed to analyze the mean scatter time? What have we done with probability? Well, the probability of a collision happening between t plus dt is also equal to the probability of collision between dt multiplied by how many molecules are there. Mathematically, we can write p of t times n sigma v dt, because n sigma v dt is the number of molecules which we have calculated. We can substitute the probability with the result we have just found. Now, finally, we arrive at the mean scatter time. The mean scatter time is actually a concept of weighted average, where the weight is the time. So it's the average time for a collision to happen, which is equal to the sum of probability times time. If we make the small time interval dt so small, we can change it to an integral. So this is the expression for the mean scatter time. I'll multiply by a factor of n sigma v so that the integral becomes very nice when we substitute with u equals n sigma vt, which is just a u substitution. Now, this integral is a well-known result. It's just 1. So we have arrived at the mean scatter time. Tau equals the reciprocal of n sigma v. So now, this is the answer to how long does it take. It is the time required between successive collisions. And hence, we have found the mean scatter time from a probabilistic perspective. I'm Delta Knowledge. See you next time.